Hi, I'm John Fowler, Executive Vice President at Sun Microsystems, and I am so excited to be here today, and I'm so glad you're joining us because we are here to talk about open storage, one of the biggest revolutions to happen in computing in more than 20 years. 10 years ago, you remember servers were all about proprietary technology, proprietary silicon, proprietary hardware designs, and proprietary software. And then the server marketplace opened up with open source technologies and new kinds of silicon and other elements of building blocks that enabled great price performance, an enormous development community, and gave spawn to whole new businesses. Well, we're here today to talk about that same revolution coming to storage. Through Sun's efforts and a large community, we are building the technology base and making it available to everyone to dramatically change the price performance of storage, the cost basis of storage, and also the community and businesses that can come up around storage. One of the reasons it's exciting is because people have been struggling with their storage infrastructure for years now, battling performance issues and struggling with the proprietary nature of how the different pieces of software interact. And so at Sun, we have been working for many years now to build a technology base which we're now making available together with programs to integrate developers and communities to completely change the landscape of storage. So I have here my guest, Jeff Bonwick, who is a Sun Fellow and nominally inventor of ZFS, the file system upon which much of this innovation is based on, and Matthew Baier, who is the lead of the community and the group that's doing the open storage community. I want to welcome you guys for joining me here and start out. And Jeff, of course, I remember years ago we talked about this and give me a little sense of what, when you started this years ago, what were you trying to solve? What was some of the issues?
I think a lot of engineering projects ultimately start in a moment of anger, when you just can't stand the things that you have to deal with in existing technology. And actually the way this began was, the genesis was really in '96. I was over in Tim Marsland's office, who's now our CTO for software. And none of the people in the building could get any work done because we were doing a big disk upgrade on our building server at the time. So we had nothing better to do than jaw about how much that made us angry. And we started to talk about this and say, you know, if you think about it, why is it like this? I mean, if you think about the way you manage memory in a system versus the way you manage storage, it's radically different. Memory is incredibly simple, right? They're both storage devices. Memory is volatile and disk is non-volatile. But other than that, fundamentally, they're both devices that can store information. And when I want to say upgrade the memory in my system,
I just add more.
You just add more.
Right.
And then, you know, maybe you have to reboot, but you power it up, it comes up, and all of your applications just get faster. Right. There's nothing for you to do. You don't have to say, now I've got to run dim config, or, you know, VI etc dim tab, or create virtual dims.
How about new FS? I have to new FS my dims.
New FS your dim, you know, new dim.
Yes.
You know. And we look at this and say, why can't we do what virtual memory did for memory? Why can't we do virtual storage? And if you actually look at the architecture of ZFS, it is very much divided along the same lines as a VM system. It doesn't really look like a storage system. It is a virtual memory analog.
So you were trying to, and this is part of the genesis of ZFS, is build a simplistic way to actually manage devices. And I know that one of the #1 topics many involved in storage is data integrity.
Yeah.
And you have a lot of thoughts on data integrity.
Yeah. Data integrity is one of those things that when you first start talking to people about it, they aren't necessarily all that interested because they figure, well, you know, it hasn't happened to me, and so I assume that it's fine. And it's one of those topics, too. It's no airline goes out and says...
Well, you may not know it's happened to you.
Or you may not know it's happened to you, or until it's too late. But it's kind of like airlines don't want to go advertise. You know, we have the lowest crash rate of any airline because you just don't even want to remind people that crashes happen. Right. It's just not a good topic. So when you remind people that disk drives actually have a published error rate, which works out to about 1 bad sector every 10 terabytes. And of course, you go back, say, 10 years.
That was a lot of memory. That was a lot of disk.
That was a lot. You're going to take you months to churn through that much data. Now, you can burn through that pretty quickly. Yeah. So you're talking about the rate that you actually encounter errors going up pretty substantially. So one of the things we wanted to do is design something that had end-to-end data integrity. Because the problem is, disk drives actually have lots of data integrity stuff in them. Right. They have all kinds of, basically the equivalent of ECC, Reed-Solomon type codes, so that they can actually, I was reading a spec sheet for a Seagate drive the other day. It can deal with a burst error of up to 320 wrong bits in a row and still correct it. Right? That's like a tenth of a sector. It's huge. Right. And yet, they're pushing the physics in these drives so hard, there's so little tolerance that they need that much error correction. And the tricks that they do inside are sufficiently complex that getting a media error these days is actually going to be fairly rare for the drive to get a media error and not detect it. But the firmware is so complex that now you have to worry about bugs in the firmware giving you bad answers.
Right, and so one of the big innovations here, and we're talking about why is this open, is you've put into ZFS, and now available in open source, the technology that actually does data integrity that in the past was only encapsulated in proprietary firmware as a part of proprietary arrays. And that's one of the things that people don't see when they first see that. And so I want to ask a question here of Matthew, and ZFS, of course, is one component. We're going to come back to a bunch of other components in open storage, and obviously that's often where conversations start because people care so much about data integrity and so on. But ZFS has actually been out in open source for some time, and let's just talk about that. I mean, what kind of communities around that? You have other companies adopting it, and what's been happening with ZFS?
ZFS is a great example. It's a core piece, like you said, of the open storage story that we're telling. It's a big part of the open storage software stack that we have on Open Solaris, and we get a lot of excitement in the community with people who realize they can do things that used to cost a lot of money in proprietary hardware all of a sudden with, say, cheap disks and a little bit of software. Yep. So, like you mentioned, ZFS is one part of a larger story we're telling, but actually it's a very, very active community on Open Solaris. In fact, it is the most active community on all of Open Solaris out there. It's got something like 1,300 subscribers. We see tremendous mail traffic. When Jeff Bonwick blogs something, people go back to Open Solaris and look at what's new. We're continuously innovating, and people are really going to the site to get the code and to build their own solutions out there. So we have a few partners that are building their own solutions. For example, a partner called Nexenta, who were one of the original participants in the Open Solaris community and built their own distribution based on Open Solaris, went a step further, and they built their own NAS software appliance using ZFS. So again, delivering breakthrough economics and without sacrificing any of the robustness or reliability.
Right. They're taking Open Solaris ZFS, they've built a bunch of administration and value add, and then they have a business around it. And that's actually the point, right? That's one of the reasons we're doing Open Solaris is we want a collection of different companies like Nexenta, and you also have end user customers pick up the Open Solaris bits. They're deploying, and one of the big value propositions, as you know, is what Jeff and the team have put together here is something that gives you data integrity and management without requiring expensive proprietary storage. And so the basic economics are just radically different for people to go pick that up. And turning to you, Jeff, a little bit here, you got rid of some headaches. Volume management was one of them, and that's also a really big thing for people that are growing storage. Yeah,
it is, because if you think about volume management, it's really not a volume is not an abstraction that is particularly natural. It's essentially a virtual disk. And for the same reason that in a VM system, you wouldn't want that, right? You wouldn't want virtual DIMMs as a programming model. It kind of looks like segmented programming, which is a real pain. And so what we did instead is said, you're going to take all the disks that you have and you just put them into a storage pool and you specify what kind of mirroring or RAID characteristics you want. But beyond that, all the stuff about how we stripe the data across it and load balance between different things, that's just all done by the software. No human intervention required.
Yeah, so I could manage it, and I do.
Maybe.
Yeah, and I have that. So I've talked a little bit about economics, and economics are an important part of this. So today, a traditional proprietary high-end array, $10 to $20 a gigabyte range for a high-end array, round numbers, $10 to $20 a gigabyte. So ZFS, similar or better levels of performance, less than $1 a gigabyte. Right. I mean, this is what we're talking about.
And that's why
it's a factor of 10.
Right. And that's what you need to do to really make an impact, I think, in our industry. Is you can't say we're going to come out and enter the storage industry with something that's 20% cheaper, because then people just look at that and say it's not worth the risk. I'm going to go with what I'm familiar with, what's comfortable. You take a zero off, and that really does change the conversation.
Take a zero off, yeah, it's 1/10. And that's what you discovered, Matthew, and people at community is this is so radical in terms of economics that people will go and run production storage on this, even though they're not necessarily, quote unquote, buying officially a storage product.
Exactly. We have one example with NeoTactics who've been using ZFS for a year, and they're very happy with it because it gives them enterprise level functionality, at not enterprise costs.
Yeah, absolutely. Well, $1 or less a gigabyte's a huge change. So, so Jeff, I think again the idea is a platform, and file systems are interesting, and clearly you have a bunch of passion about file systems. But a storage platform is a heck of a lot more than a file system. I've heard about these things called data services. Okay, snapshot restore, rollback, and so on. And so you don't have any of those. How do you have a complete storage platform?
So as it turns out, we actually do have all those things. And what's nice is that when you have it built into your core technology, as opposed to being an array vendor specific thing, you can really start to rely on it. So as a for instance, we now have ZFS boot support in Open Solaris, and we are currently doing a new package system as well that's going to be a really advanced next generation technology for managing all your package dependencies. And of course, one of the things that typically comes up is what happens if I say install some new package and it causes some sort of change to my system that I'm not happy about. And then you got to try and unwind it. Well, the nice thing about the new package system is that it is actually assuming ZFS is the root file system. So before it installs your package, it takes a snapshot of your root file system. And if you don't like the outcome, you can just roll back.
Okay, so let's get on the storage. I'm a storage IT administrator. Let's pretend for a second. Snapshot and rollback, check. You have the ability to snapshot?
Not just that we can do snapshots, but we can actually do an unlimited number of snapshots.
Okay.
So historically, the way snapshots have worked is either you can take one, or you can take up to some modest number, like 20 or 255, say. And they're taken at some fixed interval. But once you have the ability to take an unlimited number of snapshots in constant time, which ZFS can do, it enables you to do all sorts of other interesting things. For example, let's say you're managing a whole bunch of zone deployments, Solaris containers. Well, you can just create a sort of template snapshot and then clone off 10,000 of those.
Okay, so you got snapshots, and I'm going to keep you to the high level here of, I've been buying traditional arrays. I know you don't have geographic replication.
Sure do.
Okay, geographic replication.
And as a matter of fact, I'll tell you a little story about that. The guy who wrote that code, Matt Ahrens, did it while he was on a 3-month rotation in China. And actually, the reason they did it is he wanted to keep the data on his laptop in sync with his data here in Menlo Park.
So we did it across continents.
So it was across continents, and he wanted to be able to do live remote replication. It was the only way to keep his data in sync without having to, truck it back and forth. So that's actually when he wrote the code. And what he would do, just to give you a sense of how fast the snapshots are and how efficient this is, he had it take a snapshot every 10 seconds and then do an incremental send over the wire, and it goes over asynchronously, so he's not having to sit there and wait for it. So every 10 seconds, snapshot, snapshot, snapshot.
So again, I'm looking at adopt open storage platform. Protocols like NDMP. How about integration with Windows? You're not really a Windows guy. Can I integrate with Windows?
Funny you should ask. One of the great things about Open Solaris now is that we have really good integrated CIF support. And part of the issue with CIF support when it's been done in the past is that it's been done sort of as a second-class citizen, where you'd sort of translate the incoming CIF requests into things you can express in terms of the underlying POSIX file system. But there are certain things in Windows, and I'll spare you the horrible detail.
Yes, I'm going to wrap you up here.
Yeah, but things like the Windows security IDs that are actually really important in the Windows world are a somewhat stronger security model or a better naming scheme than what exists in POSIX. We actually changed Solaris to incorporate that scheme so that we can provide true native CIF support.
Right. So, Jeff, obviously you have a lot of passion about the details of things, but the idea here, it's a very complete software platform. It's not just about a file system, it's about integrating with Windows, protocols like NDMP, security technologies, geographic replication, snapshot, a whole range of things, thin provisioning.
Block storage as well. Because you can take that storage, you can export it as a file system, you can also export it as a block device, as an iSCSI target, you name it.
And it's all available as a platform. So we're joined here actually by Andy Bechtolsheim, the chief architect of the systems group, and like most things at Sun, there's a software element, there's a hardware element, and Andy, one of the things that's going on is there's also a lot of changes going on in the hardware industry that are changing economics. For example, until recently, fiber channel was really the only way to do high quality storage, and that's changing as well. So can you give us a little perspective on some changes that are happening in the industry to change price performance on storage?
Yeah, well, there's three important things. We're back to the golden era of CPU performance doubling every, let's just say, 18 months. And the great thing about having an open source software stack running on industry standard architecture is that it also doubles in performance every 18 months. Now, you realize it's not the single core performance skills, but the multi-core performance. So to take advantage of all these multiple cores, we do need a software technology that actually works on multiple cores, and Solaris CFS, the software stack, does exactly that. Now on the I/O side, SAS, single serial attached SCSI, as you mentioned, really changes the economics of the cost of the disk attach. It's basically faster and a lot cheaper than fiber channel attach. And in contrast to the good old parallel SCSI bus, which was limited to 10 feet and a couple of dozen disks, you can attach thousands of disks with SAS directly to a powerful controller, which is exactly what we intend to do. And then on the I/O side, we do need faster SAS controllers, host bus adapters, network interface controllers, but all of these are coming along, PCIe Gen 2, to support the much higher data rates that will come out of these systems. So basically, we have a fairly predictable performance curve now going forward, and the key is that the same software stack can run on a small, medium, or large machine.
Right.
And it's all at the same price performance, meaning it's not more expensive to have a bigger machine. It's actually more or less the same cost.
That's actually a good point, Andy. So if you look at today's storage hardware, to get to next levels of performance, you often have these huge incremental increases in cost that proprietary hardware gives you. You're saying that you want more performance, it's going to be much more linear.
Exactly. So traditionally, people had to design, proprietary matrix controllers, whatever they were, to get to the high performance level. And what we can see is that with the standard industry, standard architecture, we'll have better performance, more memory bandwidth, more I/O, more CPU cycles, with off-the-shelf hardware at the commodity price point.
Yeah. So one of the things that's interesting, and I know that one of the things that you're excited about is open storage. Is using an OS as its base. In this case, Open Solaris, which means that you can build and use any server at any scale that you want. Right.
Yeah, of course, this works on Spark. It works on Intel. It works on AMD. And it's all open. You can take any Sun machine, small, medium, or large, connect a lot of disk drives, and configure the amount of storage, the throughput required, depending what your needs are. I was just talking to a large government customer this morning, and they have this sort of 100 petabyte size problem that they need to solve for the next few years, and they basically cannot do it today. Both because it's too expensive and also they don't get the performance they actually need. Whereas with our open software stack, we can essentially solve these scale of problems.
Yeah, so people are looking for hundreds of gigabytes a second and tremendous performance. And now the irony is we can now start to solve that actually with commodity components, right? It's just completely upside down.
Yes, and again, this was a transition long in the making, meaning it took years for SCSI to become the standard, and then serial attached SCSI is a more recent thing. And of course, fiber channel has been out there for 15 years almost. But at the end of the day, at least my belief is economics always win the battle. Yeah. And there's no question that SAS attached, directly attached storage to general purpose servers acting as the controller is just a very powerful, very cost-effective story.
I know that both of you are very excited about a new technology that's emerging, flash memory, solid-state disk, and so on. And so, Andy, a little hardware view on how is this going to change storage?
Yeah, so we have the first solid-state disk SSD devices in-house now, and they truly are, outstanding performance. They can do 10,000 I/O ops per device, which is about, let's just say, 50 times more than a conventional disk drive. So they do win even today on a dollar per IOPS perspective. Unfortunately, they're also a lot more expensive on a dollar per gigabyte than a conventional disk. So it's kind of a trade-off. You get the performance, but you pay a premium in terms of the capacity. But we do expect flash to become much cheaper over time. So it has been on this almost free fall last year, and there's almost certainly more cost declines this year. And as the technology gets more cost effective, it will play a huge role in accelerating, in particular, transaction kind of workloads. Now the great thing about CFS, if I can make a software comment here.
Yes, of course. You guys can.
I reserve a hardware comment later.
Is that it already understands the notion of a memory cache, and we can extend extend that memory cache right into the flash. So we can actually manage the flash as it was a cache and use, so the most compelling way to use flash is basically in combination with conventional hard disks to accelerate the recently used objects and take advantage of the low cost structure of the SATA SAS drives for the bulk storage. So it's really the combination of these two technologies. And the great thing about CFS is it does this automatically, whereas in other file systems, you have to manually manage which disk gets mounted where and sort of move things back and forth.
And so, Jeff, this is one of the little secrets of our performance is you've made, or other people, not just you, have made it so that in this memory pool you can take advantage of all kinds of different storage.
Right, and in fact, if you think about going back to that virtual memory analogy we talked about before, Flash is sort of an interesting place in that the same way you have registers and caches and memory and then disk, Flash now sort of fits in the middle of that,
right,
in that it is more expensive than memory, less expensive than memory, but more expensive than disk,
right,
a lot faster than disk, not as fast as
right,
memory, but non-volatile, which is the key. And what we can do with it is two things. One is when you have a high level of write IOPS that you have to sustain, there's what we call write-biased flash, which is flash that has been optimized for taking a high level of writes into it, usually with a little bit of DRAM and supercap buffering. That we can use for providing very fast response to synchronous requests, which come up all the time in transaction processing, in NFS, any kind of network protocol where when you send the answer over the wire, it's important, as soon as that answer leaves your system, you're saying, I've committed that, so it needs to be on stable storage locally. So we can do that by using Flash as a buffer for that. The other thing that allows us to do, though, which is more of a virtual memory type analog, is that it becomes, in effect, a level 3 or level 4 cache, in that data that the file system caches in memory, we say, gee, we would love to have just more DRAM if we could, but it's really expensive. And so you can have this very, very large secondary cache. So when we evict something from our main memory cache, it now goes into this read-biased flash cache. And that gives us the ability to have, in effect, a much larger working set.
Yeah, for those people who are maybe not familiar with cache eviction algorithms, what Jeff was actually meaning to say here is when you add flash memory SSDs to a ZFS storage system, it will just go faster with no work. Right?
That sounds complicated.
Yes. So Matthew, coming back to you, we have a complete stack. I mean, what's happened is the team has put together the data services, the data integrity, all the things that you need. It isn't just about Sun's hardware. It runs on any hardware. And the interesting thing is it takes advantage of SAS and Flash and all these technologies. So what's going on? A big part of what we're talking about here is there's a community with a bunch of people, and there's a lot of projects. And give us a feel for what's happening in the community.
It's really hard to look at the community and not get excited. There's just so much enthusiasm around it. I mean, people get really passionate about ZFS, around open storage. There's quotes that we have of people who will, when it comes to storage, you will pry ZFS from a cold, dead hands. I mean, that's literally word for word what Digital said in an interview recently with us. So the great thing about the community is it's not just all Sun. In fact, there's a lot of people out there who are looking at the technology that we are providing and creating business opportunities, business value for themselves. If you look at kind of the mail traffic that's been going on, when ZFS was first open sourced, we had about 99% of all traffic handled inside of Sun. Questions and answers,
sure,
mostly responses by Sun. We're down to about 20% now. So people all around the globe are answering questions, and they're not even affiliated with Sun.
Putting their own experiences.
That's right. So the knowledge is also growing outside of Sun. It's not just the technology, and our engineers are really, really out there helping people to contribute. If you look at the kind of community leaders, it's Sun, it's other people, it's individuals, it's organizations. It really is a global community, and we're seeing a lot of interest also in high growth areas in the BRIC countries.
Sure. They're looking for that different price performance. So the other thing we've announced today is we've announced training services, professional services. Can you give us a sense of, we've moved this up a notch. It's not just people who figure out source code and work on a community, but now we've added some services here to what you can get from Sun if you want to go implement this.
Right, so one of the things that's important to see is that we have the whole portfolio. We have Open Solaris, which is sort of leading edge and gives you the latest and greatest. You also have the Solaris 10 angle, which gives you indemnification and full services. You also have developer services to help you get started. More than also just professional services, you actually have a lot of knowledge that we're making available for free.
Okay.
So if you're new to this game and you want to get started in understanding how the storage works, we have 20 hours of videos that are being made available online right now. If you're an administrator, there's white papers. If you're a developer, there's recipes to help you get you started. So you can actually get started without having to invest too heavily. And then once you get serious, as you have more money than time, you can begin then paying for
professional services for insight. So we actually have some questions from the audience here, and so they're all over the place. So let me give Andy the first question. What flash is Sun using, SLC or MLC? And you might define that for the audience. Okay,
that's actually a very good question. SLC is a single level, meaning 1 bit per transistor flash. MLC is a multi-level or several bits stored per transistor. So the flash you get in your iPhone or iPod or USB sticks are all multi-level flash, and they work fine. They have just one limitation: they only take about 10,000 write cycles, and after which they stop writing, per block. So they're not strong enough as an enterprise storage device, unfortunately. The single level flash takes hundreds of thousands of write cycles per block, and there's many blocks per device, of course. So that's the one we are using. Now the issue is that single level flash unfortunately costs more than multi-level flash. It's almost 4 times more expensive per bit, but it is still the cheaper than DRAM. So it's a very, relatively speaking, a very cost-effective technology.
Yeah. Okay. So one of the elements of open storage is obviously Lustre, which is a parallel file system that we're using on very high performance computing. And there's a question here saying, how are we integrating Lustre and ZFS?
So one of the things we didn't get into before is that part of going back to that whole VM analogy, just like in a VM system, there's the MMU, or Memory Management Unit, which takes your virtual addresses and translates them to wherever they live underneath on DIMMs, so you don't have to worry about, bank interleave and ACC and all that stuff. The DMU, or Data Management Unit, in ZFS is the really sort of core abstraction that we provide. It's a transactional object store. So the actual file system part of ZFS is fairly small. It's only about 1/10 of the code, and that lives on top of the DMU. Because if you have a transactional object store, which is basically something that allows you to say, I want to do this, this, and this to the following set of objects, and then make that happen atomically, all or nothing.
Right.
Once you have that, writing a POSIX file system on top is pretty easy. So we use that same transactional object store not only to support file systems, but also to provide volumes. And we're looking at a couple of other uses now. One, of course, is with MySQL. Now that they're part of the family, you can think of MySQL as similarly having these 2 distinct layers: a SQL engine, which deals with how do you parse the queries, and then a storage engine, which is how do I store the data. And of course, the DMU layer of ZFS makes a very natural plug-in for MySQL, so that we can then have our SQL engine on top and ZFS storage underneath. In the case of Lustre, they similarly have an architecture in which they've got a metadata server, and which sort of runs the overall structure of the file system, and then many, up to tens of thousands of data servers. What each of those data servers really needs to be, from Lustre's point of view, if they had the ideal data server, would be a transactional object store. So the way we're headed now is, and in fact Lustre even announced before our acquisition that they were transitioning off of ext3 and onto ZFS.
Yeah. In fact, I got a progress report actually yesterday. It was a trick question. They've got performance up dramatically. So I've got it's kind of an interesting thing when we talk about things for a developer. Not only have a rich storage track, but there's these different things that different kinds of developers may want to take advantage of, and people already are, which is particularly exciting. Question here for you, Andy. Where do you see InfiniBand in the scope of open storage?
That's a very good question. So in HPC, InfiniBand is pretty much the default choice these days, and it's really good at moving storage traffic, including the Lustre protocol, across the wire, primarily because it doesn't drop any packets. So in contrast to Ethernet, which is sort of a packet dropping kind of design, InfiniBand is based on credit-based flow control, similar to Fibre Channel, but it's much faster per port, and in fact has really good RDMA support to moving Lustre kind of packets around. And in fact, we get the best performance with Lustre over InfiniBand today. InfiniBand is going up to from a so-called dual data rate, or 20 gigabit per second, to quad data rate, 40 gigabits per second next year. So this is almost 4 times faster than the 10 gigabit, which is just coming along. Now, for other customers or applications, 10 gigabit may be the right answer, but certainly for high-performance computing, InfiniBand wins. Now, in the commercial setting, the traditional enterprise, InfiniBand does not have a lot of traction yet, but it does have the same kind of advantages from a cost-performance perspective.
Right.
So we're actually quite optimistic that InfiniBand will make headways into those environments, given its cost performance and just the fact that it works so well. There's another very recent development, which is a protocol to actually lay fiber channel commands directly on top of InfiniBand, known as FCOIB, and we will support that when that's available in terms of the silicon, and that will give us basically transparent block level access to storage over InfiniBand to open storage server that then provides those blocks. But you can run any protocol on top of InfiniBand.
So you're starting to spark a bunch of questions here. So first of all, on InfiniBand, we're going to spend a lot of energy here showing how people can use InfiniBand in even higher performance than what they can do today, and certainly people are already doing that.
Yes, so let me clarify a little bit here. So a large HPC cluster like the one we did at TAG has 3,900 nodes, and we had 60
petabytes of storage.
Yeah, just an enormous amount of storage and storage bandwidth. So the storage I/O on that system is about 60 gigabytes per second, and there isn't an Ethernet switch or a fiber channel switch in the country that it can deliver that.
Sustained.
So yeah, for these kind of applications, InfiniBand is a unique performance kind of metric. Now, not everybody needs 60 gigabytes per second, but the truth is, when you have that many disk drives, you actually get that much bandwidth essentially for free. And then using a fiber channel SAN that bottlenecks sort of the bandwidth is it's just not a good investment. Yeah. So in many ways, InfiniBand sort of provides to the network interface fabric the same kind of open source or open hardware attributes that we are delivering on the rest of the system.
Yeah. So one of the interesting things about the platform is, the platform we can ride on SAS, fiber channel, iSCSI over Ethernet, InfiniBand. We can take advantage of anything in the space of transport that makes sense.
Yes, of course, and I want to emphasize here, we're definitely non-religious about this. So whatever the customer thinks solves the problem the best way, we can support.
Right. So FCOE. So the question is, you brought up where does FCOE fit in?
That's another technology that was recently announced. Cisco has some products to support that. It's a little early for FCOE, meaning we think it will see more mainstream adoption in 2009, next calendar year. But it does need larger switches to make any sense. So today it's limited to very small, rack-top switches. It does not today have the scalability that you need in a large data center setting.
Right. So shifting gears here, and I have an interesting question to come back to Andy with, but Matthew, this one's for you. What geographical areas are you seeing the most traction from the community? Is there any sense of where the most interest is? And this is in the community, not necessarily products.
Yeah,
right?
so I mentioned a couple of projects that have been kicked off outside of Sun.
Yeah.
In fact, there's 6, and they're all from outside the United States.
Okay.
We're seeing a lot of interest, I mentioned, in the BRIC countries, so Brazil, Russia, India, China.
Right.
And of course, that's where a lot of the growth is, so we're trying to not only observe what's happening there, but make information access easier for those geos by translating blogs and potentially translating some of the videos that we've been shooting as educational material. So those are some of the regions where there's a lot of interest, and of course the economics play a major role in that.
Sure, and so they simply cannot afford traditional solutions to storage. So it's either do this and get on a different price performance curve, or not do anything at all. That makes it a different kind of choice as it is in a more developed country. So Andy, this is a question for you. They want to know the feature set of the next generation Thumper, and they want to know how much memory and stuff it has. Don't answer that, but they're interested. Part of the question is, getting to storage nodes that have 256 gigabytes of memory and multi-core CPUs and stuff. And are we interested in that? Are people interested in that?
There's two things going on. So obviously the upgrade path for Thumper is to go from the current dual-core CPUs to the quad-core. That's not a big secret, and that CPU will also support a lot more memory and actually a lot more I/O. So whenever that's ready, we will have a significant cost performance improvement actually, because the same box just goes faster. Now at that point, you're sort of reaching the limit of how much bandwidth you can get out of 48 disks. So future systems will actually use more like external storage units that is more scalable, mix and match up to hundreds of disks, and then these can be combined, of course, with any of the standard Sun x86 servers or x64 servers, small, medium, or large. And again, the top of the line will evolve as the CPU performance increases over time.
Yeah, so one of the things interesting, Jeff, and as you look at proprietary vendors that may in fact have proprietary hardware or their own operating systems, they don't scale. So this fellow was asking about, having storage controllers with 256 gigabytes, and that's kind of a medium amount of memory, right? But terabytes of memory or wherever, I mean, we can just scale, right?
Yeah, and in fact, one of the things that really has turned out in Solaris's favor over the last 5-10 years is that if you remember toward the end of the 90s, we were just building ever bigger and bigger vertically scaled system, and then all of a sudden the bubble popped and everybody wanted these really cheap one-use systems. Right. And we were sort of wondering for a while about all that work that we did on scalability in Solaris to scale up to 64-way and larger systems. Was that all just kind of a wasted effort? Nobody wants those anymore. Well, fortunately, what's happened in hardware design is that the clock rate used to be going up just along the same line as Moore's Law. In fact, it was even super exponential during the 90s. But it sort of peaked at around between 2 and 3 gigahertz, and it's pretty much flattened out for about 5 years. But we're still getting more transistors, and there's sort of a point of diminishing returns in dedicating those transistors to ever more on-chip cache. So you get to the point where you say, gee, the actual computing core on this die is only 3% of the real estate. Why not have 2? Or 4, or 8, because it's a small percentage. So what we've seen, of course, we were the first with Niagara with the 8-core design and 4 threads per core. So you had a 32-threaded system on a single die at 65 watts, 2 watts per thread, pretty amazing. And now we've seen that Intel and AMD have followed suit, and everyone is now going down this path of ever more cores. And all that work that we did, and it took us 10 years to do, to get Solaris to scale to that many cores, that much concurrency, all that work is now paying off for us in a big way.
And so in the storage platform, you can use any scale of head end you want. You map memory, so many gigabytes, terabytes, doesn't matter.
Exactly, and one of the reasons that people often do storage clusters today is precisely because you can't take a sort of primitive custom real-time OS and say, I'm going to scale that up to this kind of memory, this kind of level of threading. So you have to have clusters of smaller machines, and of course that's actually harder to manage than a single system image if you can get away with it. And we can provide now really large head-end systems, not that are big refrigerator-sized computers, but things that actually fit in a couple of rack units. Yeah. Right? And really, the compute's all on one socket. It's just amazing.
So one of the capabilities of doing the open storage platform is people can develop to, and then we can scale not just on Sun hardware, on anyone's hardware to different sizes, but we're also working on PNFS,
Indeed.
which will let us scale horizontally. And so just give us 30 seconds on PNFS.
I was going to put a time limit on me now.
Yeah, no, I need to shorten you up.
So the beautiful thing about PNFS is that people have wanted clustered solutions for a while for when a single system doesn't provide enough scale, when you really want tens of thousands worth of nodes. The problem is that all of those solutions to date have been proprietary. What PNFS is going to provide the industry is the first ever standardized clustering solution.
Okay.
So it's an IETF standard, and it has a very similar architecture to Lustre. In fact, we're converging our efforts on those projects so that we have a very mature PNFS implementation from day one. But that really allows you to scale just as large as you want to go.
So this idea here is adopt the open storage architecture with this. You can make any head end whatever scale you want using whatever hundreds or thousands of drives, and then the PNFS gives us the ability to then scale horizontally.
Exactly.
Which is, you want the hundreds of gigabytes per second solved. That's fine. You want to do 1 million IOPS. We can do it. You can scale in any direction. So we got another question here from the audience here, which is related to your thing. Will NFS v4.1 or PNFS be available with ZFS? Okay, so I understand there's a little confusion here between the two of them, so you have to explain the difference, right?
Yeah, so PNFS is really a network protocol that runs on top of some underlying local file system. So there's some file system for the basic components of PNFS, or what they call a metadata server, which is the thing that knows the structure of the data, and then lots of data servers behind that. And each one of those can actually run any file system. So you can run it on top of, Linux with ext3. You can run it on ZFS, on UFS, QFS, whatever you like. But there are certain advantages to be had in having the data servers actually know or not be full POSIX file systems, but just be these simpler transactional object stores. So the way we're designing the PNFS code, just like we're looking at with Lustre and with MySQL, the PNFS code already in its development has a direct DMU client,
right,
so that we talk right to that transactional object store for maximum speed.
Yeah, we have another developer question that's related here, and you can actually do yes or no to this one if you want. Is the DMU layer available to developers? Can anyone decide they want to write an application to talk to the DMU? You've mentioned several examples.
Absolutely. It isn't a completely stable API at this point, in the sense that we expect that we're going to change it somewhat over time. Right. Of course, the OnDisk format is stable; that has to be. But the number of DMU clients we expect to be, initially in the order of, half a dozen to a dozen, and hopefully I'm wrong by 2 zeros on that. But at least initially, we'll have a relatively small community of people who are developing these, and that actually will drive the evolution of those interfaces.
Right. So I think your friends must be asking some of these questions. We got some trick questions here. I'll answer some of these. Any plan to open Sun's grid up in a matter of Amazon to let us use open storage on demand? And the answer to that is stay tuned. Clearly, open storage is very well suited to providing a very high scale storage on demand service, since we can both change the price point of how you can deliver that service, as well as scale both vertically and horizontally in an open way. It's absolutely ideal for building a storage on demand type of services. So stay tuned on that one. There was a question here, community question for you, Matthew. What are a few examples the community is doing? You mentioned some companies, but just a couple of examples.
So we've got some companies, we've got some individuals. Maybe start with some of the individuals.
Right.
Projects that were created outside of Sun, which are exciting because many of these individual developers come from the Linux world.
Right.
So they're looking for this familiarity. They want to create projects that make it easier for people to transition over to OpenSolaris. And they have projects like JFS, which is run by somebody, I think, also in Brazil. You have EXT3, which of course is the Linux file system that is being ported over to OpenSolaris. We have SquashFS, which is a compressed read-only file system, and projects like this, which again are driven outside of Sun, which is for me always a validation that if we had not open sourced OpenSolaris and the open storage stack, none of these projects would even exist. In terms of companies, we have certainly customers who are deploying this today. We also have an example, Live Ammo, who are producing instructor-led courses around virtualization and enterprise storage. And so they were looking around at creating some kind of storage appliance in the back end. They looked at the Linux model, it didn't work for them, they couldn't get the numbers to work, so they ended up using ZFS again and the open storage stack to build their solution.
So Andy, there's a general question here for you. Is just, what kind of response from customers do you see on sort of the open storage thing? And again, live global webcast, maybe you can't mention the customers, but I know you are talking to customers every single day about both the hardware and software and all these pieces, and what kind of responses are you getting?
Well, everybody's interested in cost performance and scalability, right. So that goes without saying. And there are some questions: is this really stable? Is this ready to deploy? And maybe people want to turn on 100 petabytes the next day, but there's a lot of interest in getting going now with smaller scale and then going to bigger scale deployments. And I'm not sure there's a single thread to accept the performance angle where people are just running out of bandwidth on existing solutions, and to get more performance would be so expensive that they just don't have the budget.
Right. Well, one of the other things is also, I like to think of there's three broad areas. There's people that run very stable business applications infrastructure. There's people that are building internet infrastructure, and people building HPC. And in those other two, current conventional proprietary storage solutions are where they aren't finding what they want, and those are where you end up having most of your conversations.
That's a very good point. So the way to think about the market segmentation is that there's the high growth, lots of petabytes, lots of scale demand market, and then there's a more traditional enterprise market where it grows incrementally.
Right.
So clearly the interest coming from the high growth people that want tons of storage.
Tons of storage, great. So there's a question here about, and this is kind of for both of you, so maybe we'll start with Andy. Is there a project to optimize open storage for use with databases?
Well, I guess this is the other feedback we have been getting from certain customers. They realize that they actually have much more access to the content of the stored bits if they run the database directly on the storage controller, because you don't have to go through the fiber channel or any other network, between the database layer and the machine. Now there is some software optimization in the plans that Jeff can talk about, but from a hardware perspective, what people want in that application is just more cores. So they, the number of cores within Thumper is not nearly enough really to enable those. And one interest in these very more scalable machines, using them as a storage headend, is actually to enable transactional and other searching kind of applications that can just scan through all the storage and at the wire speed of the disk interface rather than the speed of the SAN network.
Yeah. So Jeff, you've talked about the DMU and stuff, but I think there's a lot of other stuff around different kinds of applications. Traditional block mode storage today is about high-speed random I/O.
Right.
There's lots of other kinds of applications like streaming media and things like that. And how well does open storage relate to these kinds of different applications, which is what often these two other groups are thinking a lot about?
Indeed, and it actually works really well in those applications. I would say actually that in some ways the most demanding workload is actually the database workload, precisely because you have all this random I/O that you have to deal with. And that's where you really do want some kind of hardware support. If you're performance sensitive, you want something to help you deal with those synchronous I/O requests, make them go real fast. And that's where these solid-state disks and flash technology are just such a huge advantage for us. The way people have dealt with this in the past is they've used NVRAM, non-volatile memory, which is very expensive, and it's typically only non-volatile for a relatively small amount of time, basically the lifetime of the battery. And in many cases, you're only good for a few days. Right? And we actually had instances of people losing data after the World Trade Center event because of batteries dying. The nice thing about flash is that when you write to flash, you're physically changing the material. You don't need battery support for it to stay alive. And it's also much cheaper than NVRAM. And there's no battery that has to be serviced. So what we're doing in building these systems that have flash, to Andy's point about the sort of mix and match aspect of it, you've seen some of the drive vendors put flash inside disk drives to optimize like boot time, that sort of thing. But then you've got a fixed ratio of flash to size of the platter. But we want to be able to dial that around. So we're mixing simple, cheap disk drives with as much or as little flash as you need for your particular application.
And so transactional random I/O, big streaming read files, any of those kinds of applications, we got a fairly complete platform to actually go and take care of. So I want to, go ahead, Andy.
This is particularly interesting to Web 2.0 companies that typically have a database kind of layer that they want to run really fast to be responsive to customers coming on the web, whereas you put the images or the videos or the music into conventional disk drives. So it's really again a combination of flash for transactional and disk for bulk storage that makes the most sense economically speaking.
Yeah, and again we have a platform that can handle all that. So little forward view, and without of course disclosing any product direction, since it's a worldwide telecast, but Open Solaris is kind of a server operating system, right? And I'm kind of used to managing my storage differently. Are we working on the management story without providing screenshots or products there?
Without providing screenshots, boy, are we working on the management story. And of course, it would be one thing to say, gee, we're going to come up with a really pretty user interface to allow you to manage all this and point and click and have it be simple. That would be a great thing. But why stop there? Why not take advantage of the fact that we have this very powerful operating system underneath with things like dtrace built in and FMA built in for monitoring faults, so that what we're actually doing is taking advantage, for example, of when a disk drive starts to fail. The FMA subsystem in Solaris notices this and tells ZFS, hey, I've done the diagnosis, and based on what I'm observing, this disk is bad or this controller is bad. And then that gets integrated into the management stack we're developing and becomes ultimately a notification to the administrator of what corrective action needs to be taken. That's part number one. Part number two that's really powerful is the business analytics that you can do with dtrace. You don't actually have to know dtrace to use it. It's all sort of a point-and-click model, but you can look at a system and say, gee, all of a sudden it's not as responsive as it was before. What's happening? And you get in, you look at it, and you say, oh, I'm getting a whole bunch of traffic from this client. And what are they doing? Oh, it's on this file. And we've already used this internally to debug some very surprising problems. And in contrast to existing storage technologies, which tend to be very much black boxes, if you've got a filer sitting there not performing well, you have no idea why.
Right, right. So one of the things is, and again, having seen this technology myself, is the open storage platform. We talk a lot about price performance, cost performance, the fact it's open and runs on a variety of hardware. But there's these other things that we've been working on, which, like ZFS, give us some breakthrough capabilities. And certainly forensics and visibility is a huge one. We're going to be able to provide people's visibility in the systems like they've never seen before.
Absolutely. And one of the things that I think is most compelling about it is that how many times have you had this sort of a scenario where you notice that there's some hiccup in performance and you say, ooh, I got to figure out what that is. You go, you log in, you get yourself all set up, you got all your diagnostic tools, you're ready to go, the problem goes away. And you know it was a real problem, but it's gone now. The beautiful thing about the analytics that we're building is that you can go back in time to when the bad thing happened and do the drill down from there. So we're gathering, because dtrace is so efficient, we can gather all this forensic information on a continuous basis so that you can go back and say, at 2:30 this morning, some bizarre thing happened. What was that?
Yeah. Well, I've seen demonstrations of this stuff, and it's really exciting. And since you and I have both been with customers that have seen some of this, and they've been really startled, because when you hear about open storage, you just assume it's missing a lot of stuff. But as we talked about, very complete platform, highly scalable, works across a range of hardware, includes forensics and other things that people don't want. And as Andy talked about, leverages SAS, fiber channel, InfiniBand, gigabit Ethernet, 10 gigabit Ethernet, surfs on multi-core CPUs. And I guess the question for you, Matthew, is how do people get started? I mean, this sounds like a big grand revolution, and
we're trying to
I'm excited. What do I do, right?
We're trying to keep it as simple as possible for people to get engaged. So I mentioned some of the educational material that we have available. We're going to be producing many more. Today is one day in a rolling out of much more material. And there will be storage administration wikis. There will be a lot more information available also for developers to understand and get their hands into the code. But the real call to action is join the community.
Right.
Once you're part of that community, you can communicate directly with Sun engineers. There's a large team at Sun actually engaging with the community. There's Jeff Cheney, who's the facilitator of the open storage platform. He's very well known and plugged into the community as well. So get on the mailing list, monitor what's happening, and contribute as you can.
So we have a website, sun.com/open storage, and what you're going to see on the website there is all of the things we talked about here today, which is the principles and capabilities of the open storage platform, the communities and how you join the communities and interact with them, the products that you can either download or interact with or buy today in both hardware and software, all of the professional services as well as teaching materials. So if you need storage assessments or you want developer assistance or developer training, it's all on sun.com/open storage. And again, it is about being an open platform. It isn't just about Sun's hardware, it's about everyone's hardware, and it's about really building a completely new world in storage with dramatically better economics and cost performance and dramatically better capability for developers. So anyway, we're excited to be here, and we really hope to see you soon on the open storage community. And I'm John Fowler. Thanks for joining us. Okay, great.